Alright, so now you've gotten the hang of Lewis stat structures. Now we're going to apply them to actual three-dimensional geometric shapes. So what we call these shapes of molecules is pronounced VSEPR. It doesn't look like VSEPR, but it is. Trust me. VSEPR. Valence shell electron pair repulsion. Alright, so what that means is when a molecule is formed from the different atoms, the atoms are going to try to get as far away from each other as possible. Okay, they don't be jammed in too close. All right, so they're just going to take that whole three-dimensional spacer and spread themselves out as far as possible and create these different geometric shapes. Typically, when you look at the Lewis stat structure, you can get an idea of what the shape of the molecule is supposed to be, or the specific shape. And so these VSEPR shapes gives a molecule more of a three-dimensional shape. Right, now on my website I have a couple tables for the shapes and the bond angles, plus I showed you that website from PhET, which also you can figure out a lot of different molecules and their shapes, but we'll go over how to draw some of them. Right, first one is the easy one. We're going to do what's called a linear molecule. Right, linear is nice and easy. So if we look at BeI2, right, if you do a Lewis stat structure, beryllium iodide looks like this. Okay? And as you can see, that's a linear shape because the two iodines are as far apart from each other as possible. So that's our Lewis stat structure for this. Okay? Now, coincidentally, or not, to sketch the shape of the molecule, it's really exactly like the Lewis stat structure. Just like that. Alright, so that's the shape. That's the linear shape. Yeah, they look exactly the same. And the way you draw the shape, just like how we did here, you have the bonds here, and in place of the atoms, you just do the symbols. So you don't have to do any of the circles or anything like that that you might see in some pictures. For grading purposes and when you do the homework, that's perfectly fine. All right. So that's your linear molecule. Now, water, let's take a look at that. So if we do a Lewis stat structure for water, oxygen's in the middle with its 6 valence electrons, and hydrogen. All right. Now this cannot be linear because, you know, what's oxygen have that beryllium doesn't? Yes, you guessed it. Oxygen has these extra electrons here. Those 4 extra electrons are 2 pairs. All right, so what those pairs are going to do, they're actually going to bend the hydrogens down a little bit, kind of push them down, make them more of an angle. So when we sketch the shape, instead of looking linear, it's going to look like this. All right, and these electrons are pushing the hydrogens down. So saying electrons, since they're free electrons, they tend to be a little stronger. So they got a much stronger push. They'll kind of squeeze those hydrogens a little bit closer together. So that's the difference between linear and this shape, which is called angular or bent, whichever one you want to say. All right, so it's angular or bent, that's the shape of molecule. And yeah, the main difference is the unshared pairs of electrons. Without them, it's a linear. With them, it is angular. Now, our next two examples, kind of similar there. First one, we're going to look at boron BF3, boron trifluoride. Now remember, boron, another exception to the octet rule, only has 6 valence electrons. I'm sorry, only has 3 valence electrons, so it can hold on to 3 atoms. Only has 3 bonding sites. So here's your BF3. Okay. And again, this is your Lewis stat structure. So now if you look at this, look how this molecule looks. As you'll see, got all this open space up here. All right, here you have like 90-degree angles down here. These fluorines are kind of close to each other. All this wide open space. So what those two fluorines are going to do is they're going to kind of move up just ever so slightly, get a little bit farther away from this fluorine at the bottom. So what it'll look like is kind of like a Y shape. Now that's not the name. This isn't Y shape. That's not the name. The name for this is trigonal, because you got the three F's, the three outer atoms there. Trigonal, and we call it trigonal planar because it sits flat on a plane. So there's trigonal planar. Now, let's look at an F3. We do that Lewis dot structure. All right, so here's your nitrogen. That's 5 valence electrons. I think you know where I'm going with this. F, F, and F. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right, so here's your NF3. So again, what does nitrogen have that boron doesn't have? Of course, nitrogen has those extra electrons there. So what are they going to do? Just like what did the oxygen do with its extra electrons? You are right, of course. What they're going to do is these fluorines are going to kind of get pushed down and make kind of like a little tripod there. So it's going to look like something like this. And now this is the scientific bad artist way of drawing this. We're going to do our two F's like that. So those are kind of pushing down. Okay. Now imagine a tripod. If you look at a tripod, you got the two legs down, and you have like the third leg, and it kind of looks like it's sticking out at you. We're going to draw something like that here. So what we got here is, for this third fluorine, we're going to draw a kind of like a shaded in triangle like that. All right. So that thing right there, that shape means coming out of the screen. We'll say that. Like it's coming out at you. All right, so it's sticking out just kind of like imagine a tripod, and that middle leg is sticking out towards you. So that's the shape. That's how the shape works. That's the scientific bad at artistry rendition of three-dimensional shapes. And the name of this shape, well, since just like the one on the left, we'll say trigonal, but it's not on a plane. We're going to say it's trigonal pyramid, because it kind of takes on the shape of a pyramid there. So trigonal planar and trigonal pyramid. Again, the main difference is, just like in the two we did before, the main difference is you got lone pair of electrons here pushing the atoms down, whereas here there are no lone pair of electrons, so these kind of go up to fill in that empty space. All right, the fifth one, we're going to do CH4, methane. So carbon's in the middle, that's got 4 lone electrons. And the hydrogen is going to attach to each of those. All right. So this is your Lewis dot structure. So the shape, this is going to get kind of funny here, guys. Here's what this shape's going to look like. So your carbon's in the middle. And those two hydrogens look something like that. Right. Now the other two, think of them as more three-dimensional. So this bottom one, kind of like with the NF3, that's going to be coming out at you. Now with this other hydrogen, we're going to represent that. We're going to show that as going into the paper, like going away from you. So do that. kind of make like a little dashed line, make them small so that kind of looks like a triangle going away from you. And there you go. The name of this molecule is tetrahedral. Tetrahedral because it's got 4 atoms surrounding that center atom. Right? And all 4 of these, if you can imagine like 3-dimensional space, they're all kind of all scattered in 3-dimensional areas, as far apart away from each other as possible. So that's your tetrahedral. So those are the main 5. Okay, now we do have a couple others we'll show you. I'll just show you here, and then there's others on the table you can look at. We look at PCl5. Remember, phosphorus here is going to go against the octet rule. So if we do our Lewis stat structure, oops, 1, 2, 3, 4, 5, Cl, Cl, Cl. Well, these other 2, remember that unshared pair of electrons kind of splits up and makes 2 extra bonds there. All right, so 3-dimensionally, this is what this guy is going to look like. You got your phosphorus in the middle. 1 Cl's on top, 1 Cl's on bottom, so that's 2 of the 5. Okay, the other 3 kind of going to circle around the phosphorus here, kind of like a propeller. So there's your 1 Cl. This one is going into the screen. That one's coming out at you. So there you go. Now, shape-wise, the name of this shape, well, think of this. This is kind of making a little triangle, right? So kind of like trigonal, and that might be in the name. If you connect those and those, just kind of imagine 2 pyramids where the bases kind of attached to each other. The apexes, apices, whatever. They're on the opposite ends. Right? This we call trigonal, because you got the triangle. Trigonal bipyramid. You write that a little better. Say trigonal bipyramid molecule. Again, because you got the trigonal, the 3 in the middle there, and it makes 2 pyramids. Alright, so I get rid of some of these lines so it looks a little better. There you go, trigonal bipyramid right there. And now we'll take it 1 step up here. We're going to do SF6, sulfur hexafluoride. So if we do that shape, like we did before, there's sulfur 6, 1F, 2 Fs. These split up to make another 2 fluorines. Those split up to bond to those 2. Here's your SF6. There's your Lewis stat structure. Okay, shape-wise, same thing as before. 1F on the bottom, 1F on top. And now you got 4 more. So those 4 kind of go around propellers just like this. So yeah, so you got those 2 over here. That's kind of what we're going to do over here. We're going to put another F there. And F there. So there's your 4. 5. And 6. Voila. So now naming. You might think, kind of keep it similar as the last time, you might think, oh, instead of trigonal bipyramid, because yeah, let's connect the dots here. Put these together. If I could draw accurately, that would make a square. And you connect all those. All right, a common name, not the correct one, but a common one would be square bipyramid. Kind of makes sense, right? Because this is trigonal bipyramid, because you got the triangle and the 2 pyramids. Square bipyramid, because you got the square, and there's your pyramid, there's 2 pyramids there. So okay, makes sense. The real name what's supposed to be is octahedral. That's the name of the shape. I don't know if anybody will take square bipyramid, so call it octahedral. So octahedral is because, if you look, it's got 8 faces. So when you connect everything, it kind of looks like an 8-face diamond or a 8-face jewel. Or if you're into some of these board games, like I was into Dungeons and Dragons when I was a kid, it's like an 8-sided die. So there's your 8 sides there. So that's where you get your octahedral. And the very last common one we'll do, again, there's a couple others you'll research in your notes. The last one we have is xenon tetrafluoride, XCF4. So we're going to do this Lewis structure. 8 electrons are on xenon. Looking good. So, shape-wise, all right. So this is going to be actually pretty similar to the octahedral did before, except for instead of an atom on top and atom on bottom, they're replaced by unshared electrons. But going around there, you got your fluorines. Right? So the name of this one, well, it makes a square. And since it lays flat on a plane, called square planar. Right? So those are the most common shapes of molecules you need to know. And now there's a few others. And again, if you go on my website, I have the table of different shapes. Or if you did that PhET simulation when you're going through the homework, you'll see a few of those too. All right, so but these are the most common, so these you should definitely know. Now the last spin-off, which you'll see here, is something like this. I'm going to talk about 3-dimensional shape of methanol, CH3OH. All right. Now, in all the other ones we did before, we had a center atom. There's no center atom here. So what we're going to do is we're going to kind of split it up into parts. So we'll say that this molecule here is a combination of different VSEPR shapes. All right, first one is, well, we'll look at this, focus on this carbon right here. So let's assume this carbon is the center atom. So you see carbon, 1, 2, 3, 4, has its 4 bonding sites. Right? If you ignore this hydrogen here, pretend it's not there, what do you think this looks like? Yeah, so this is a tetrahedral area, if you will. Because it has the 4 areas, it looks just like a tetrahedral. Okay. Now on this side here, what kind of area does that look like? Yeah, well, here's your oxygen. There's your 4 electrons, 2 other bonds there. So that kind of looks like the bent area. So you can take parts of a molecule and just kind of divide them up and say, okay, this is a tetrahedral area, this is a bent area, one area could be a trigonal pyramid area. So just kind of focus on one atom and look around it as if that was your center atom, and just pick that part and match it up with the shapes that you learned before. And that was the different shapes of the molecules, different VSEPR shapes.